Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is Thevenin's theorem and the maximum power transfer theorem as applied to AC circuits. Our objective is to examine several illustrated examples of Thevenin's theorem and the maximum power transfer theorem. Additionally, each illustrated example problem will feature an extended play bonus round where we discuss the physical construction of a Thevenin's equivalent circuit, the determination of the Norton's equivalent circuit using a source conversion, and impedance matching using transformers. This lecture operates under the presumption the viewer has more than a passing familiarity with both the Thevenin's theorem and the maximum power transfer theorem as illustrated in the AC Thevenin's theorem and the AC maximum power transfer theorem lectures, both available at the Big Bad Tech channel. If you lack the requisite level of familiarity with these topics, please review the aforementioned supporting material and return to this lecture when you are so qualified. If you've been following this playlist in its intended sequence, you are no doubt aware that Thevenin's theorem is a procedure that simplifies a complicated series parallel circuit into an equivalent simple series circuit. The original and the Thevenin's equivalent should ideally behave the same, and importantly, the variable load impedance should be none the wiser to the substitution. Of note is not only the substantial ease with which calculations can be made using the simple Thevenin's equivalent circuit, but also how much less components, connections, and confusion is involved in the physical construction of the Thevenin's equivalent circuit. The Thevenin's equivalent circuit consists of a single AC voltage source called ETH in series with a single impedance, ZTH, in series with a variable load impedance, Z load. To simplify a complicated circuit into its Thevenin's equivalent, we need to solve for these two quantities, ETH and ZTH. Additionally, you are no doubt aware that the AC maximum power transfer theorem states the maximum real power will be transferred to a load when the variable load impedance equals the complex conjugate of the Thevenin's equivalent impedance. Mastery of Thevenin's theorem and the maximum power transfer theorem necessitate active participation on your part, and as such, I'm encouraging you to please pause the lecture when asked to do so and attempt the example problems on your own. If your answers do not match those illustrated, by all means, feel free to rewind the lecture and correct any mistakes you may have made. Our first example problem features a series parallel combination of four elements. The first element, Z1, is a non-ideal inductor that presents a complex impedance of 172 ohms at an angle of 83 degrees. The second element is a capacitor that presents a complex impedance of 600 ohms at an angle of negative 90 degrees. The third element, Z3, is a resistor that presents a complex impedance of 400 ohms at an angle of 0 degrees. And the fourth element is our variable load impedance, Z load. The sinusoidal AC voltage source has an effective value of 120 volts and an excitation frequency of 60 Hz. Stage 1 of this example problem necessitates we solve for the Thevenin's equivalent circuit seen by the variable load impedance. Once we've got these values, we'll move on to stage 2 and examine maximum power transfer for this circuit. By all means, pause the lecture and try stage 1 on your own. If you're tracking, you should have obtained the following results. Let's first solve for the Thevenin's equivalent voltage, ETH. To solve for ETH, one removes the load impedance from the nodes of interest. Then, one determines the open circuit voltage seen across the nodes of interest. Let's start by removing the variable load impedance Z load. Note the removal of the variable load impedance has fundamentally altered the nature of our original series parallel circuit. Now we need to determine the open circuit voltage seen across our nodes of interest. It appears our open circuit voltage of interest is the voltage across the parallel combination of impedance element Z2 and Z3, a simplification I'm calling Z single prime, where Z single prime equals 332.8 ohms at an angle of negative 33.7 degrees. Our imagined combined impedance Z single prime is in series with impedance element Z1. Perhaps the easiest and most direct means of solving for our voltage of interest is the AC voltage divider rule solving for V single prime. Substituting in our given values yields 133.9 volts at an angle of negative 31 degrees. Let's set these calculations aside and move on to solving for the Thevenin's equivalent impedance, ZTH. Solving for the Thevenin's equivalent impedance, ZTH, also necessitate the removal of the load impedance. Additionally, one must also remove the source, or sources, from consideration. One removes a voltage source by replacing it with a short circuit or zero impedance path. One removes a current source by replacing it with an open or an infinite impedance path. Finally, one determines the impedance of this modified circuit at the terminals of interest. Make note that ZTH is not the impedance seen by the original source. ZTH is the impedance seen by the load impedance when the source has been removed. Let me remind you that incorporating shorts and opens inside your original series parallel circuit and shifting perspective from the source to the load may fundamentally alter the nature of the original series parallel circuit. Let's start by removing the variable load impedance, Z load. Let's now remove the voltage source by replacing it with a short or 0 ohm impedance path. Now we need to determine the impedance at the nodes of interest. The incorporation of the short circuit has effectively placed impedance elements Z1, Z2, and Z3 perfectly in parallel with one another, a simplification I'm calling Z double prime, where Z double prime is our Thevenin's equivalent impedance of 192 ohms at an angle of 52 degrees. The Thevenin's equivalent circuit for this first illustrated example problem is therefore the series combination of ETH at 133.9 volts at an angle of negative 31 degrees and ZTH at 192 ohms at an angle of 52 degrees in series with our variable load impedance Z load. Stage 2 of this illustrated example problem now dictates we determine the load impedance which receives maximum real power. Additionally, see if you can solve for voltage across the load, current through the load, and apparent, real, and reactive power for the load at conditions of maximum power. By all means, pause the lecture and try stage 2 on your own. If you're tracking, you should have obtained the following results. The AC maximum power transfer theorem states that maximum real power will be transferred to a variable load impedance when the variable load impedance equals the complex conjugate of the Thevenin's equivalent impedance. Therefore, our variable load impedance should see maximum real power when it has a value of 192 ohms at an angle of negative 52 degrees. An application of the AC voltage divider rule suggests voltage across the load at maximum power conditions is 108.7 volts at an angle of negative 83 degrees. A subsequent application of Ohm's law suggests current through the load at maximum power conditions will be 566.4 milliamperes at an angle of negative 31 degrees. A phasor diagram illustrates current through the load leads voltage across it by a relative 52 degrees. Using only this relative phase shift, the AC power formula suggests that the load experiences 61.6 volt amperes of apparent power, of which 37.9 watts is directed towards real power and negative 48.5 VARs is directed towards a reactive interchange. Given this represents maximum power conditions, any change in load impedance magnitude or angle should result in less real power delivery. Before we move on to the next illustrated example problem, let's try a quick extended play bonus round for this first illustrated example. Let's say we're being tasked to build the Thevenin's equivalent circuit at maximum power conditions using real-world components. Stage 3 of this illustrated example problem now dictates we determine the component values which will create the Thevenin's equivalent impedance and the variable load impedance at maximum power conditions. By all means, pause the lecture and try stage 3 on your own. If you're tracking, you should have obtained the following results. Obviously, there's no such thing as a complex impedance of 192 ohms at an angle of 52 degrees on the shelf of the complex impedance store downtown. There are, however, resistive and reactive elements that when connected in a series fashion can present a complex impedance of 192 ohms at an angle of 52 degrees. Given our desired Thevenin's equivalent impedance has a positive angle, we're most likely dealing with a resistor in series with an inductor. Resolving the Thevenin's equivalent impedance expressed using polar format into its resistive and reactive components expressed using rectangular format yields a value of 118.2 plus J151.3. This implies that our Thevenin's equivalent impedance is a 118.2 ohm resistor in series with an inductor that happens to have an impedance value of 151.3 ohms at our given excitation frequency of 60 Hz. Algebraically rearranging the inductive complex impedance formula to solve for inductance and substituting in our given values yields an inductance value of roughly 401.3 millihenries. These two elements in series act as our Thevenin's equivalent impedance ZTH at the given excitation frequency of 60 Hz. Let's do the same thing for our variable load impedance, Z load. Again, there's obviously no such thing as a complex impedance of 192 ohms at an angle of negative 52 degrees in the supply shelf. There are, however, resistive and reactive elements that when connected in a series fashion can present a complex impedance of 192 ohms at an angle of negative 52 degrees at our given excitation frequency. Resolving the load impedance at maximum power conditions, expressed using polar format, into its resistive and reactive components expressed using rectangular format, yields a value of 118.2 minus J151.3. This implies our load impedance at maximum power conditions is a 118.2 ohm resistor in series with a capacitor that happens to have an impedance magnitude of 151.3 ohms at our given excitation frequency of 60 Hz. Algebraically rearranging the capacitive complex impedance formula to solve for capacitance and substituting in our given values yields a capacitance value of roughly 17.5 microfarads. Alright, I believe we've accomplished our desired goals, including an extended play bonus round, and can now move on to our next illustrated example problem. Our second illustrated example problem features a series parallel combination of 4 elements. The first element, Z1, is a complex impedance of 24 ohms at an angle of 50 degrees. The second element, Z2, is a complex impedance of 40 ohms at an angle of 0 degrees. Our third impedance, Z3, is a complex impedance of 36 ohms at an angle of negative 30 degrees. Our fourth element is our variable load impedance, Z load. The voltage source has an effective value of 50 volts at an angle of 0 degrees. Stage 1 of this illustrated example problem necessitates we solve for the Thevenin's equivalent circuit seen by the variable load impedance. Once we've got these values, we'll move on to stage 2 and examine maximum power transfer for this circuit. By all means, pause the lecture and try stage 1 on your own. If you're tracking, you should have obtained the following results. Let's first solve for the Thevenin's equivalent voltage, ETH. To solve for ETH, one must remove the load impedance from the nodes of interest. Next, one determines the open circuit voltage seen across the nodes of interest. Note the removal of the load impedance may fundamentally alter the nature of the original series parallel circuit. It appears our open circuit voltage is the voltage across impedance element Z3. Perhaps the easiest and most direct means of solving for our voltage of interest is the AC voltage divider rule, solving for V3. Substituting our given values yields 24.5 volts at an angle of negative 15.8 degrees. This is our Thevenin's equivalent voltage, ETH. Let's set these calculations aside and move on to solving for the Thevenin's equivalent impedance, ZTH. Solving for the Thevenin's equivalent impedance also necessitates the removal of the variable load impedance. Additionally, one must remove the source, or sources from consideration. One removes a voltage source by replacing it with a short. One removes a current source by replacing it with an open. Finally, one determines the impedance of the modified circuit at the terminals of interest. Again, make note that ZTH is not the impedance seen by the original source. ZTH is the impedance seen by the load impedance when the source has been removed. Incorporating shorts and opens inside the original circuit and shifting perspective from the source to the load may fundamentally alter the nature of the original series parallel circuit. In this occasion, the short has effectively removed impedance element Z1 from consideration, and impedance element Z2 and Z3 are in parallel with one another. Taken in parallel, this combination presents an impedance of 19.6 ohms at an angle of negative 15.8 degrees. The Thevenin's equivalent circuit for our second illustrated example problem is therefore the series combination of ETH at 24.5 volts at an angle of negative 15.8 degrees, and ZTH at 19.6 ohms, also at an angle of negative 15.8 degrees, in series with our variable load impedance Z load. Stage 2 of this second illustrated example problem now dictates we determine the load impedance which receives maximum power. Additionally, see if you can solve for the voltage across the load, current through the load, and apparent, real, and reactive power for the load at conditions of maximum power. By all means, pause the lecture and try stage 2 on your own. If you're tracking, you should have obtained the following results.